In this section, we'll consider what it means to have cheap, abundant energy. It's not an exaggeration to say that we use energy for everything. For example, in cutting wood, we can either use an axe with body energy or a chainsaw powered by fossil energy, because it's easier and quicker. Of course, all the energy we use is ultimately derived from the sun, from the food we consume to the many machines we operate. The three images depicted here show the historical progression of the primary energy sources, from human labor to animal labor, and culminating with fossil-fueled machines. This chart illustrates individual energy consumption over time, beginning with cave folk and ending with the modern era, circa 1950. On the far right of the chart is the total amount used measured in gigajoules. A gigajoule is 1 billion joules, and 6 gigajoules is about how much potential chemical energy there is in a barrel of oil. At the upper left, you see the color codes for the different areas in which the energy is consumed. Black is for food, blue for domestic services, green for industry and agriculture, and yellow for transportation. Notice the exponential curve. What does that say about fossil fuels and the ease of life we live, when compared to, for instance, the developed farmer? At the bottom, an illustration compares energy use between rich and poor worldwide. Roughly 1/4 of the world's population, the rich, uses 3/4 of the energy produced, whereas 3/4 of the population uses 1/4 of the energy. Clearly, there is a connection between the amount of energy used and the relative degree of wealth comfort. This experiment illustrates the energy used to power a single light bulb using human labor. Here you can see a bicyclist pedaling continuously to keep a 100-watt bulb lit. So, what about producing enough electric power to handle the typical requirements of an average U.S. household? Well, it's estimated that it would take approximately 50 bicyclists to run all appliances and lights, dishwashers, microwaves, refrigerators, air conditioners, and so on. Just imagine how much it would cost to hire 50 energy-producing workers, even if paying a minimum wage. Anyone who has ever had to push a car can appreciate the crucial role of gasoline. It's estimated that to push a car the same distance a gallon of gas would move it, say 20 miles, might take approximately 500 hours. And if hiring someone to push it at the rate of $10 per hour, it could cost around $7,500. Furthermore, if you add the hidden cost of road maintenance, traffic controls, and so on to the price of a gallon at the pump, then the total cost might run $15 plus per gallon. Because we rely so heavily on fossil fuel energy, we are naturally concerned about the amount of remaining world supplies. And because oil is our primary fossil fuel, we'll focus on it. This chart shows global oil discoveries and production since 1950. The tallest green line represents 1964, the year of greatest discovery. Since then, discoveries have been declining up until the present era, when, depending on the year, we use from 2 to 4 times more oil than we discover. How long do you suppose this can last? One way to consider oil extraction is through the EROEI method, which stands for Energy Returned on Energy Invested. It's essential to determine the net energy gained in any oil project, which is measured by estimating the energy used in extracting the potential energy contained in any discovered oil project. Since the 1930s, the EROEI ratio has steadily worsened. As you can see, the ratio dropped from 100 to 1 in the 1930s to 25 to 1 in the 1970s. However, the upside-down hockey stick indicates a precipitous decline due to the exponential factor, this time dropping to 0. So what does this mean? As we go deeper in the ground or underwater, or as we strip mine for tar sands in Alberta, the energy requirements increase until the return is a mere 3 to 1 ratio. The energy cost associated with discovering and extracting new oil projects now stands at 30%, indicating that the overall energy available to the larger economy is severely diminished by 30%. As a point of reference, the feudal economy of early medieval Europe had an estimated available energy ratio of 1.2 to 1, or 20% surplus energy to use as needed. With 70% surplus energy, we are much better off now, but we still need to be concerned about the growing cost of energy. This resource extraction profile provides a graphic summation of the oil depletion process. The overarching bell-shaped blue line indicates the depletion curve of all oil production over time, while the smaller bell-shaped curves along the bottom indicate the individual oil fields. Moving left to right, colors of the bell curves change from green to red, representing the increasing challenges of extracting oil in discovered fields. The green and yellow lines represent rising cost and energy intensity. The apex of the large curve could be the year 2005, 2010, or sometime in the future. But as we shall see in the next chart, it's highly probable that peak oil is past tense. This chart, provided by the Energy Information Agency of the U.S. Department of Energy, shows the annual energy outlook from 2009 to 2030. It projects the depletion rates of existing oil fields, along with the types of projects that might replace that production rate. The colored fields indicate the current depleting fields, and it clearly suggests that production levels will decline. The big white space, labeled unidentified projects, the peak oil community calls the wedge of hope. Even though these new projects have yet to be identified, the EIA dubiously estimates that production will increase from 88 million barrels per day to 105 million by 2040, a mission we think is impossible. As this chart shows, it is immediately apparent how much the world depends on the big three fossil fuels: coal, gas, and oil. It's important to remember that these finite energy sources cannot be replicated as cheaply, easily, or productively using renewable energy technologies. For instance, in terms of primary energy sources, the nuclear hydro segment makes up a surprisingly small portion of all output. At the top of the chart, the tiny sliver represents what is termed as renewables. Note how energy production drops from 2008 to the present. One fact that obscures the date of peak energy production is the recession that began in 2007, because energy production always falls when demand slackens. It's obvious that depending on renewables to replace the big three fossil fuels is proving unwise. Each type of renewable has its drawbacks, but all share some common problems. For instance, it takes lots of fossil fuel energy, rare earth materials, and money throughout the entire process of designing, manufacturing, transporting, marketing, and maintaining high-tech equipment. Moreover, each type of renewable might work well in some locations, but not in others. And transmission of energy to some locations is very expensive, primarily due to inadequate power grids. Here's a chart depicting U.S. energy consumption by sources. Prominently viewed are the big three, comprising 83% of the pie, plus nuclear at 9% and renewables at 8%, broken down into 7 types. It's especially interesting to learn that wood provides the U.S. with more energy than the top 4 renewables combined. Also, note that while the use of wood and hydroelectric power is nothing new on the energy landscape, they can't be considered viable in terms of replacing fossil fuels. The renewables that the national interest is pinning its hopes on are the top 4, especially wind and solar. This unique chart compares the energy equivalent produced by a cubic mile of oil, approximately the amount the entire world uses in a year, to other energy production sources. These other energy sources represent what would be needed to replace just 1 year of oil use. The black numbers inside the red circles indicate how many of each energy source is needed every year for 50 years, while the yellow numbers represent the sum total of the black number multiplied 50 times. For example, to replace 1 cubic square mile of oil will require 104 coal plants each year for 50 years, for a total of 5,200. It's also worth noting that not one of these non-oil sources is a liquid fuel, a unique critical property that high-density oil has over all other energy sources. A common confusion involves distinguishing between energy and technology. While both terms are often used interchangeably, they are in fact distinct, as this chart illustrates. It's especially important to remember that energy cannot be created, only gathered, stored, transformed, and conserved. The energy cycle involves 3 steps. First, it is sourced, then utilized, and finally dispersed. We've already mentioned a few drawbacks to specific alternative energy sources, but here are some general considerations. Commercial energy transitions take at least a generation to develop and mainstream. Substitutability or replacement of infrastructure is typically required, and it takes huge amounts of time and money. Rare earth elements are required, iron ore, copper, oil, and so on, most of which are getting harder and more expensive to find and process. The inconsistency of wind and sunshine are real problems, and they are confined to specific geographical areas. Energy density is exceptionally low for renewable energy sources, unlike high-density fossil fuels. Much water is required in most operations. For example, 2,000 plus gallons are used to produce 1 gallon of ethanol, and in the Alberta tar sands, 3 barrels of water are used for every barrel of synthetic oil produced.